The foundational crisis. At the turn of the 20th century, math was in trouble. It was undergoing what came to be called the foundational crisis of mathematics. At the time, set theory had come to serve as the foundation of mathematics. All mathematical proofs ultimately relied on it. But in 1899, Ernst Zermelo noticed this set theory had a fatal flaw. Zermelo told other math professors at the University of Göttingen about it, including David Hilbert, but Zermelo didn't publish it. In 1901, Bertrand Russell also noticed this flaw. But Russell didn't stay quiet. He wrote a letter in 1902 to Gottlob Frege, just as his second volume on set theory was going off to the publisher. Frege had spent decades laying the foundation of set theory. It was his life's work. But one letter, showing one flaw, brought it all down. Russell showed Frege's set theory allows two contradictory statements to both be proved. This flaw is known as Russell's paradox. One flaw might not sound so bad, but in math it is fatal. For if in math, just one falsehood can be proved, then any falsehood can be proved. This is known as the principle of explosion. For example, assume mathematics had a flaw that allowed you to prove that 2 plus 2 equals 5. You could use this false proof to prove anything. You could prove that the $1 in your bank account equals $1 million. Starting with 2 plus 2 equals 5, subtract 4 from both sides. Then you get 0 equals 1, now multiply both sides by 999,999. Then you get 0 equals 999,999, now add 1 to both sides. You have now proven 1 equals 1 million. If math allowed proofs of false statements, then contracts, commerce, even society as we know it, couldn't function. This was the state of mathematics in 1900, it's no wonder it was considered a crisis. Math was broken. It had to be fixed. It needed a rallying cry. A call to action. In 1900, mathematicians from around the world gathered in Paris for the International Congress of Mathematicians. David Hilbert, considered the greatest mathematician of his time, was invited to speak. He used the opportunity to present what he considered to be the 23 most significant open problems in mathematics. The second of Hilbert's problems called for a proof that the foundational rules of mathematics were free of contradictions. This would, once and for all, put math on a solid foundation. Never again would mathematicians need worry that a new contradiction might one day surface and torpedo the whole of mathematics. New foundations. The collapse of Frege's set theory and Hilbert's call for a provably solid foundation for math served as an inspiration. Under Hilbert's direction, Zermelo began work on fixing set theory. Similarly, Bertrand Russell began work with his supervisor, Alfred North Whitehead, on a solution. Their aim was to lay a new foundation for mathematics based on a precise logic, and produce a set theory rid of paradoxes and contradictions. It was a massive undertaking that took over a decade. It culminated in the 3-volume tome Principia Mathematica, published in 1910, 1912, and 1913. It was so detailed, that it famously required several hundred pages to work up to the point where it proved 1 plus 1 equals 2. Owing to its complexity and unique notation, Principia Mathematica never gained much popularity with mathematicians. It also had a competitor. By 1908, Zermelo developed a new set theory, consisting of just 8 rules. And in 1921, it was further improved by Abraham Fraenkel. Their combined result is called Zermelo-Fraenkel set theory. It became the default foundation of mathematics, and remains so to this day. Hilbert's program. although no one had discovered contradictions in either Russell's or Zermelo's new foundational systems, no one had been able to prove they were free of contradictions either. Mathematics still rested on a foundation of uncertain stability. This led Hilbert, in 1921, to push for finding a mathematical theory that was provably consistent. And not only did he want this theory to be provably consistent, he wanted it to be provably complete. A complete system of mathematics means any true statement can be proven within that theory. There would never be a need to add to this complete theory, as it would cover everything that mathematicians might think up in the future. It would be a final theory and the last theory any mathematician would ever need. It was the mathematician's equivalent of a theory of everything, where all of mathematics is derivable from one rock-solid foundation. The effort to find this theory became known as Hilbert's program. It was a noble goal. But less than a decade after launching his program, Hilbert's dream of a final theory was shattered. In 1930, at a conference in Königsberg, Hilbert remained confident in the eventual success of his program, proclaiming, "Wir müssen wissen. Wir werden wissen, we must know. We will know." The phrase would later be Hilbert's epitaph. Gödel's incompleteness theorems. Unknown to Hilbert, his dream had already been crushed. The day before, at the very same conference, the 24-year-old Kurt Gödel presented his PhD thesis. It proved Hilbert's dream is impossible. At the conference, Gödel presented his first incompleteness theorem. It showed that in any finite mathematical foundation, there will be true statements that can't be proved in that theory. Thus Hilbert's dream of completeness is impossible. Quote, "The most comprehensive current formal systems are the system of Principia Mathematica, PM, on the one hand, the Zermelo-Frankelian axiom system of set theory on the other hand. These two systems are so far developed that you can formalize in them all proof methods that are currently in use in mathematics, i.e. you can reduce these proof methods to a few axioms and deduction rules. Therefore, the conclusion seems plausible that these deduction rules are sufficient to decide all mathematical questions expressible in those systems. We will show that this is not true." End quote. Kurt Gödel in On Formally Undecidable Propositions of Principia Mathematica and Related Systems 1, 1931. Gödel's first incompleteness theorem showed there could never be a final theory that would serve mathematicians for all time. Gödel wasn't finished. Shortly thereafter, he published his second incompleteness theorem. This proved that no consistent theory of mathematics can ever prove itself to be consistent. The second of Hilbert's 23 problems was impossible. This explained the failure of Zermelo in proving the consistency of his set theory. It was actually a good sign that he was unable to. Had he been able to prove it consistent, it would imply that it was not. So now, not only was completeness impossible, but it was also impossible for a theory to prove its own consistency. This was a double whammy to Hilbert. Hilbert lived another 12 years, but he never publicly acknowledged Gödel's result. Privately, he was crushed. He didn't want mathematics to be this way. But others greatly admired Gödel and his achievement. When Harvard gave Gödel an honorary degree, he was introduced as the discoverer of the most significant mathematical truth in the century. Some called Gödel the greatest logician since Aristotle. Edward Nelson called Aristotle the greatest logician before Gödel. John von Neumann said, "Gödel is absolutely irreplaceable, he is the only mathematician alive about whom I would dare make this statement." Einstein and Gödel both worked at the Institute for Advanced Study. Near the end of his life, Einstein confided to Oscar Morgenstern that his own work no longer meant much, that he came to the Institute merely to have the privilege of walking home with Gödel. Undecidability. In 1673, Leibniz invented and later built the first digital calculator. He declared, "It is beneath the dignity of excellent men to waste their time in calculation when any peasant could do the work just as accurately with the aid of a machine." After he built the device, Leibniz began to wonder about the limits of what machines can calculate. Was it possible to build a machine that could answer any mathematical question? Several centuries later, David Hilbert together with Wilhelm Ackermann refined Leibniz's question. At a conference in Berlin in 1928, they defined the Entscheidungsproblem, or decision problem. The decision problem asks, is it possible to build a machine that can decide whether or not any mathematical question can be proved in some mathematical system? Gödel showed that not every true statement was provable, but was there a way to decide whether or not a statement was provable? It was an important question. Such a method would be most useful to mathematicians. It would tell them when they ought to give up, and thereby save them from wasting their lives searching for proofs that don't exist. Alonzo Church got the first result on the Entscheidungsproblem. He defined a programming language, and proved certain questions about it are undecidable. Quote, "It follows that the Entscheidungsproblem is unsolvable in the case of any system of symbolic logic which is consistent, in the sense of Gödel." Alonzo Church in An Unsolvable Problem of Elementary Number Theory, 1935. The next year, Church's student, Alan Turing, published another example of an undecidable problem, the halting problem. Quote, "Gödel has shown that there are propositions U such that neither U nor, not U, is provable. On the other hand, I shall show that there is no general method which tells whether a given formula U is provable." Alan Turing in On Computable Numbers, with an application to the Entscheidungsproblem, 1936. It was in this paper that Turing introduced the concept of a general-purpose programmable computer, birthing the digital age. Hilbert never got the answers he hoped for. We can't prove the consistency of a mathematical foundation. We can't prove everything that is true, and given undecidability, we can't even be sure whether a statement has a proof or not. And yet, despite not getting the answers he hoped for, Hilbert knew the right questions to ask. The answers produced great discoveries. Quote, "I'd like to make the outrageous claim, that has a little bit of truth. That actually all of this that's happening now with the computer taking over the world, the digitalization of our society, of information in human society, you could say in a way is the result of a philosophical question that was raised by David Hilbert at the beginning of the century." Gregory Chaitin in A Century of Controversy Over the Foundations of Mathematics, 2000. Hilbert's 10th problem. Of Hilbert's 23 problems, his 10th problem asked for a general method to solve Diophantine equations. These are equations that allow only whole numbers, no decimals or fractions, which are named after Diophantus who studied them in the 3rd century. Quote, "Given a Diophantine equation with any number of unknown quantities and with rational integral numerical coefficients, to devise a process according to which it can be determined in a finite number of operations whether the equation is solvable in rational integers." End quote. David Hilbert in Mathematical Problems, 1902. Deceptively simple Diophantine equations were often notoriously difficult. A famous example is the Diophantine equation. A to the power of n equals b to the power of n plus c to the power of n. This equation is easy when n equals 1, or when n equals 2. Millennia ago Pythagoras proved there were infinite solutions when n equals 2. And yet, no one had found even one solution for n greater than or equal to 3. No one knew of a cube number, a to the power of 3, that was the sum of two other cube numbers. In 1673, Pierre de Fermat wrote in his notes that he had a proof that there were no solutions when n greater than or equal to 3. But no one had ever found it, nor was anyone able to rediscover a proof. The missing proof became known as Fermat's last theorem. The problem went unsolved for 321 years. Until in 1994, after 7 years of work, Andrew Wiles completed a 129-page proof that no whole number solutions exist when n is greater than or equal to 3. If mathematicians had a procedure to solve Diophantine equations, Andrew Wiles wouldn't have had to spend 7 years working on this problem. Instead, he could program a computer to follow the procedure and the computer would crank out a solution. In 1970, Hilbert's 10th problem was solved. Solving it required 21 years of work by 4 mathematicians, Martin Davis, Julia Robinson, Hilary Putnam, and Yuri Mashjasevic. Their proof, called the MRDP theorem, after their initials, gave a negative result. They proved there is no general procedure for solving Diophantine equations, and they proved it in a shocking way. They showed an equivalence between solutions to Diophantine equations and what is computable. In other words, for any imaginable computer program, there is a Diophantine equation whose solutions equal all the outputs of that computer program. This was so surprising that many mathematicians had difficulty believing it. It meant there is a Diophantine equation that picks chess moves like Deep Blue, and there's a Diophantine equation that does your taxes like TurboTax, and there's yet another Diophantine equation that does spell checking like Microsoft Word. For anything a computer can compute, there's a Diophantine equation that gives the exact same answers. But despite how surprising their result was, it was true. And this is why there can be no general method for solving Diophantine equations, because the question of whether or not a program finishes Turing's halting problem is equivalent to asking whether or not some Diophantine equation has solutions. Since the halting problem is not generally solvable, the equivalence between Diophantine equations and computers meant Diophantine equations weren't generally solvable either. Yet again, what Hilbert asked for couldn't be provided. Hilbert's questions probed at the heart of consistency, provability, decidability, and computability. They didn't lead where he expected, but they did reveal deep truths about the nature of mathematics. Universal equations. In 1978, the mathematician James P. Jones went a step further. Just as it is possible to make a computer program that runs all other computer programs, it is also possible to make a Diophantine equation that includes all other Diophantine equations. Quote: Mashjasevic's theorem implies also the existence of particular undecidable Diophantine equations. In fact, there must exist universal Diophantine equations, polynomial analogues of the universal Turing machine. End quote. James P. Jones in Undecidable Diophantine Equations, 1980. Such Diophantine equations are general-purpose computers. Plug in the program as one of the variables to the equation, and the solutions to the equation will be the outputs of that program. Jones provided an example of such an equation. It is complex, but the truths concerning this single equation include all truths concerning the executions and outputs of all computer programs. Quote: As v varies through the positive integers, the equation defines every recursively enumerable set. This is, to our mind, the attraction of the universal equations. At once, this equation defines primes, Fibonacci numbers, Lucas numbers, perfect numbers, theorems of ZF, or indeed theorems of any other axiomatizable theory. James P. Jones in 3 Universal Representations of Recursively Enumerable Sets, 1978. We might consider such universal equations as God equations, equations whose solutions contain and include all the others. In his 1987 book Algorithmic Information Theory, Gregory Chaitin describes one such equation, the exponential Diophantine equation computer. It has 20,000 variables and is 200 pages long. This equation perfectly replicates the behavior of the Lisp programming language. He describes the equation as follows. Quote, if the Lisp expression k has no value, then this equation will have no solution. If the Lisp expression k has a value, then this equation will have exactly one solution. In this unique solution, n equals the value of the expression k. End quote. Gregory Chaitin in Meta Math. The Quest for Omega, 2004. Chaitin showed that even modern-day computers and programming languages have counterparts in the form of Diophantine equations. Universal Diophantine equations are remarkable. They exist in pure arithmetic. The arithmetical relations they encode represent every program that can be computed along with all of their outputs. Among these solutions we can find the valid proofs of every theorem in every mathematical system, every way of playing every computer game that has or will ever be invented, and simulations of every galaxy in the observable universe down to the atomic level. Universal Diophantine equations contain in their solutions everything computable. Since known physical laws are computable, quantum-detailed histories of every particle interaction in the observable universe are counted among these solutions. Jones's discovery of universal Diophantine equations inspired him to quote chapter 11, verse 7 of the Bhagavad Gita, "Whatever you wish can be seen all at once right here." This universal form can show you all that you now desire. Everything is here completely. Given that such equations include everything computable, including all physical laws and systems as well as simulations of any observer's mind and brain, could these equations be the glue connecting eternal mathematical truth with contingent physical truths? The Universal Dovetailer. In 1991, Bruno Marchal wrote a program he called the Universal Dovetailer, a program that generates and runs all programs. In order to run every program without getting stuck on a program that never ends, the Universal Dovetailer interleaves, or dovetails, on the processing, doing a little bit of work on each program at a time. The program is simple. The full program is quite short, consisting of about 300 lines of Lisp code. Its pseudocode is even simpler. For k from 0 to infinity. For j from 0 to k. For I from 0 to j. Compute k steps of program I on input j. This program sequentially generates every program and runs it for every input. The longer the Universal Dovetailer runs, the more programs it generates and the more steps of each program it performs. If allowed to run forever, it runs every program there is. The Universal Dovetailer, like a fractal, is itself simple and yet it generates infinite complexity. In the words of Plotinus, for that which generates is always simpler than that which is generated. 270 AD. This program, like universal Diophantine equations, contains all. While studying the consequences of the existence of all computations, Marchal made an incredible discovery, what he describes as the many histories interpretation of elementary arithmetic. The discovery served as the basis of his 1998 PhD thesis, Computability, Physics, and Cognition. This paper explains how we can explain the appearance of a multiverse given two assumptions. 1. All computations exist. And 2. Computation supports cognition. Quote, we will explain that once we adopt the computationalist hypothesis, which is a form of mechanist assumption, we have to derive from it how our belief in the physical laws can emerge from only arithmetic and classical computer science. Bruno Marchal in the Computationalist Reformulation of the Mind-Body Problem, 2013. Given there exist universal Diophantine equations, all computations exist as a consequence of arithmetical truth concerning them. While there is no physical realization of the perpetual execution of the Universal Dovetailer, its complete execution exists in number theory as a consequence of arithmetical truth. There are, for instance, Diophantine equations whose solutions exactly equal all the sequentially generated states reached by the Universal Dovetailer. So if we accept the self-existent truth of 2 plus 2 equals 4, we must also accept truths concerning universal Diophantine equations, truths that concern all computational histories and all simulated realities. Quote, "To be sure, the existence of the UD is a logical consequence of elementary arithmetic with Church's thesis or Turing's thesis." End quote. Bruno Marchal in Discussion List, 2019. It therefore becomes a purely mathematical question to prove whether some Diophantine equation contains in its solutions a computational state equivalent to some person's physical brain state. We would then exist for the same reason that 2 plus 2 equals 4, as an inevitable consequence of mathematical truth. The question why is there anything at all is reduced to why does 2 plus 2 equals 4. A story of creation. We have arrived at a plausible story of creation. We can now connect the causeless abstract entities, logic, truth, and numbers, with a viable cause for our perceptions of a physical reality. Why does anything exist? Because necessity requires logical laws. Logical laws imply incontrovertible truth. Such truth includes mathematical truth. Mathematical truth defines numbers. Numbers possess number relations. Number relations imply equations. Equations define computable relations. Computable relations define all computations. All computations include algorithmically generated observers. And these observers experience apparent physical realities. Ancient anticipations. This account of how eternal mathematical truths could give rise to contingent physical truths depended on recent discoveries. It required a deep understanding of modern ideas, universal equations, computers, computation, virtual reality, and simulation. Only a century ago, we didn't even have words for these concepts. Despite this, a few ancient thinkers gave theories for existence that are eerily similar to this modern creation story. They postulated something primal and simple that gave rise to the numbers, and from numbers arose beings, consciousness, and matter. 2,600 years ago, Lao Jia wrote that numbers proceed from the Tao, and that from numbers that all things are born. Quote, "The Tao gives birth to one. One gives birth to two. Two gives birth to three. Three gives birth to all things." Lao Jia in chapter 42 of Tao Te Ching, circa 600 BC. Diogenes Laertius was a biographer of eminent philosophers. The following is his account of 2,500-year-old Pythagorean beliefs. Quote, "That the monad, one, was the beginning of everything. From the monad proceeds an indefinite duad, two, which is subordinate to the monad as to its cause. That from the monad and the indefinite duad proceed numbers. And from numbers, signs. And from these last, lines of which plane figures consist. And from plane figures are derived solid bodies. And from solid bodies sensible bodies." End quote. Diogenes Laertius in the Lives and Opinions of Eminent Philosophers, circa 225 AD. 1,750 years ago, Plotinus developed Neoplatonism, a rich theory concerning the relations between various levels of being. Wikipedia describes Plotinus's chain of being as a series of emanations. The first emanation is Nu, divine mind, logos, order, thought, reason. From Nu proceeds the world soul. From the world soul proceeds individual human souls, and finally, matter, at the lowest level of being and thus the least perfected level of the cosmos. Quote, "The One is not a being but the generator of being. The greatest, later than the one, must be the intellectual principle, and it must be the second of all existence. For what emanates from the intellectual principle is a reason principle, a logos. And as soon as there is differentiation, number exists. Thus number, the primal and true, is principle and source of actuality to the beings. The soul's substantial existence comes from the intellectual principle. The soul, itself a divine thought and possessing the divine thoughts, or ideas, of all things, contains all things concentered within it. This gives the degree in which the cosmos is ensouled, not by a soul belonging to it, but by one present to it. It is mastered not master, not possessor but possessed. This one universe is all bound together in shared experience. So matter is actually a phantasm. Plotinus in the Enneads, 270 AD. 1570 years ago, Proclus wrote that mathematical existence occupies a middle ground. He said mathematical being sits between the simple reality that's grounded in itself and the things that move about in matter. Quote, mathematical being necessarily belongs neither among the first nor among the last and least simple of the kinds of being, but occupies the middle ground between the partless realities, simple, incomposite, and indivisible, and divisible things characterized by every variety of composition and differentiation. The unchangeable, stable, and incontrovertible character of the propositions about it shows that it is superior to the kinds of things that move about in matter. But the discursiveness of mathematical procedure, in dealing with its subjects as extended, and its setting up of different prior principles for different objects. These give to mathematical being a rank below that indivisible nature that is completely grounded in itself. Proclus in a commentary on the first book of Euclid's Elements, circa 450 AD. The causeless cause found. Could this be the answer? Could things be so simple? In order for this explanation of existence to be correct, mathematical truth must be causeless. Mathematical existence must depend on neither human minds, nor on physical or material things. In addition, mathematical truth must be something capable of generating observers who consciously perceive their environment, and which they consider as existing physically. Ideally, this causeless cause will illuminate the relation between the mental and material, and explain why the universe obeys simple laws. Can the theory achieve this? Is it causeless? For mathematical truth to serve as a causeless cause, it must exist causelessly. Math must depend on neither minds nor matter. Independent of minds. Do numbers and their properties exist beyond the minds of mathematicians and their scribblings on blackboards? Had Hilbert's program succeeded, and given a mathematical theory capable of proving all true statements, then arguably, mathematics might only be that which follows from this theory. Math would then be an invention of the human mind. But the failure of Hilbert's program, and Gödel's proof of the impossibility for any finite theory to define all mathematical truth, meant that mathematical truth is infinite and beyond description, and therefore cannot be a product of human minds. Quote, the existence of absolutely undecidable mathematical propositions seems to disprove the view that mathematics is only our own creation. For the Creator necessarily knows all properties of his creatures, because they can't have any others except those he has given to them. So this alternative seems to imply that mathematical objects and facts, or at least something in them, exist objectively and independently of our mental acts and decisions. That is to say, it seems to imply some form or other of Platonism or realism as to the mathematical objects. Kurt Gödel in Some Basic Theorems on the Foundations of Mathematics and Their Implications, page 311, 1951. C. Is math invented or discovered? Independent of matter. The infinite nature of mathematical truth also implies an independence from matter. Our observable universe has an information capacity of 10 to the power of 120 bits. This number is large, but finite. Nowhere in physics is there room to store, represent, or hold the infinite true statements of mathematics. If there are infinite primes, infinite factors of 0, infinite digits of pi, they don't exist physically. If these infinite properties don't and can't depend on physical processes operating within a material universe, it follows that mathematical properties must exist independently of matter. Quote, "It is our firm belief that the Pythagorean theorem needs not be created, nor the fact that the circumference of a circle is 3.14, and so on, times the diameter. The laws of nature and the collection of truths, values and their interrelations are primordial, and have always existed." C.W. Ryatishkin, Four-Dimensional Reality Continued, 2018. Is it the cause? For this story to work, abstract objects, truth, numbers, equations and so on, must play a causal role in generating reality and perceptions. The default position of philosophers has been that abstract objects have no effects, they cause and do nothing. But we must admit that this has always been an assumption, it's never been proven. Quote, "Although philosophers deny that abstract objects can have causal effects on concrete objects, abstract objects are often defined as causally inert, their potential, say as a collective, to be an explanatory source of ultimate reality cannot be logically excluded." End quote. John A. Leslie and Robert Lawrence Kuhn in The Mystery of Existence, 2013. Recent advances in mathematics give us pause. The discovery that all computations exist as a consequence of mathematical truth, makes us wonder whether abstract mathematics is really so ineffectual. But can mind or matter really be created by math? The cause of minds. Consciousness remains one of humanity's last great mysteries. While science has not settled the question of what consciousness is, it has progressed by developing a testable theory of consciousness. In the 1600s, thinkers such as René Descartes and Thomas Hobbes advanced the idea of mechanism, the theory that our brains and bodies are machines that operate according to mechanical rules. In 1936, the discovery of universal machines, or computers, led to the Church-Turing thesis, which says the behavior of any finite machine can be perfectly replicated by an appropriately programmed computer. This is their special power. It is what makes computers so useful. Without changing your computer's hardware, it is able to run any one of the millions of applications available to it, including applications not yet developed or conceived of. Each new application provides the computer with new functionality and behaviors. Some were quick to recognize the implications of the Church-Turing thesis for theories of minds, brains, and consciousness. The two fathers of computing, Alan Turing and John von Neumann, noticed parallels between computers and the mind. In 1948, Turing wrote the first chess-playing program, and in his 1950 paper Computing Machinery and Intelligence, Turing asked, "Can machines think?" The last work of John von Neumann was a lecture series, The Computer and the Brain, published posthumously in 1958. In it von Neumann explains that it is not that the brain acts like a computer, but that computers are so varied in what they can do, that they can be set up to imitate any machine, presumably even the human brain. Quote, "The important result of Turing's is that in this way the first, universal, machine can be caused to imitate the behavior of any other machine." John von Neumann in The Computer and the Brain, 1958. In the 1960s and 1970s, philosophers of mind including Hilary Putnam, and his student Jerry Fodor developed what they called functionalism. In its digital form, functionalism is known as the computational theory of mind, or computationalism. This is the idea that function, or computation, is the foundation of consciousness. The computational theory of mind remains as the most popular theory for consciousness among scientists and philosophers. Quote, computationalism, or digital mechanism, or simply mechanism, is a hypothesis in the cognitive science according to which we can be emulated by a computer without changing our private subjective feeling. Bruno Marchal in The Computationalist Reformulation of the Mind-Body Problem, 2013. If the computational theory of mind is true, then mathematics can explain where observers come from. Observers would be found among the infinite computational histories within arithmetical truth. See, what is consciousness? And can a machine be conscious? Recent discoveries in physics lend support to computationalism. In 1981, Jacob Bekenstein discovered a physical limit now known as the Bekenstein bound. This bound says that a physical system of finite mass and volume can contain, at most, a finite amount of information. This applies to any finite physical system, a brain, the Earth, the solar system, our galaxy, or the observable universe. Given that the observable universe has a finite mass and volume, it follows by the Bekenstein bound that it has a finite description. Given that it has a finite description, it follows by the Church-Turing thesis that the evolution of the observable universe is something that is perfectly replicated by a certain computer program. This program contains a version of you, me, the Earth and everyone and everything present in our universe. Our shared histories and memories would be identical. But the question remains, are these computational doppelgangers conscious like we are? If we inspected the contents of this computer program, we would find analogues of all the objects of our own universe. We would find the same books, articles, and movies. Among these we would even find many works on the mysterious nature of consciousness. These same books will also appear in a purely computational version of our universe, written by computational authors, who apparently are just as baffled by their conscious experiences as we are. If these purely computational versions of us are not conscious, what drives them to write and read books about consciousness? If, on the other hand, they are just as conscious as we are, then the idea of a separately existing physical reality becomes redundant. In that case, for all we know, we are these computational versions. We would then exist as pure computations. We would inhabit the computational histories of simulated realities that exist only as a consequence of mathematical truth concerning universal equations. Every imaginable computation is realized in arithmetic as true relations about these universal equations. This includes the computations that describe you, your environment, and even the evolving state of your brain as it processes this very sentence. If computationalism is right, this is who we are. Quote, we'll explore the fascinating relations between computation, mathematics, physics and mind, and explore a crazy-sounding belief of mine that our physical world not only is described by mathematics, but that it is mathematics, making us self-aware parts of a giant mathematical object. Max Tegmark in Our Mathematical Universe, 2014. The cause of matter. Can mathematical truth, with its inherent infinite collection of computational histories, explain matter, physical laws and universes? How can abstract things, like truth, numbers, computations, give rise to concrete things like chairs, bricks, and houses? What's the difference between abstract existence versus concrete existence? Some say the difference is only a matter of perspective. To a being who inhabits an abstract object, be it an abstract mathematical object or abstractly existing computation, it seems concrete to them. Quote, this equivalence between physical and mathematical existence means that if a mathematical structure contains a self-aware substructure, it will perceive itself as existing in a physically real world, just as we do. End quote. Max Tegmark in The Mathematical Universe, 2007. The relative aspect of concrete existence, is explicit in Marcus Muller's definition of physical existence. Quote, "Given two objects A and B, we say that they physically exist for each other if and only if, under certain auxiliary conditions, modifying the state of A will affect the state of B, and vice versa." Marcus Muller in Could the Physical World Be Emergent Instead of Fundamental, and Why Should We Ask? 2017. Whenever a conscious observer experiences or interacts with another object, that object appears concrete to that observer, even if, from another point of view, both that observer and object seem abstract. Of the modes of existence, this understanding implies mind over matter. Math produces an infinity of conscious minds, and the perceptions of these minds include experiences of material realities. Computationalism, together with the mathematical existence of all computations, leads to a causal reversal between mind and matter. Quote, "What results is not a primitive matter with consciousness emerging from its organization but the reverse. Consciousness is now the more primitive and matter, or rather the appearance of material organization, emerges from all the possible experiences of all the possible consciousnesses." End quote. Bruno Marchal in The Amoeba's Secret, 2014. Matter is then, as Plotinus supposed, a phantasm. Is this testable? This is a big pill to swallow. Are we to take as serious the idea that we live inside an equation? And this equation somehow produces all computations by virtue of its solutions? And that the whole physical universe is just some kind of shared hallucination? Extraordinary claims require extraordinary evidence. Unless there is a way to test and either confirm or falsify this theory, we are not operating in the realm of science, but fantasy. Fortunately, there is a way to test this theory. Due to the fact that not all programs appear with equal frequency, a particular bias should appear in the resulting computational histories. We can then check for this bias by comparing our observations of the character of physical law and the properties of our universe against the predictions made by the theory. Not all predictions of a theory are necessarily testable, but the more predictions of a theory we test and confirm, the more our confidence in that theory grows. If our observations match the predictions, we gain evidence in support of the theory. If they don't match, we rule the theory out. This is how all theories are tested. Algorithmic information theory. The reason not all programs occur with equal frequency is due to a consequence of algorithmic information theory, or AIT. This field was developed by Ray Solomonoff, Andrei Kolmogorov, and Gregory Chaitin, starting in the 1960s. Chaitin says, AIT is the result of putting Shannon's information theory and Turing's computability theory into a cocktail shaker and shaking vigorously. The basic idea is to measure the complexity of an object by the size in bits of the smallest program for computing it. Across the infinite programs executed by universal equations, some programs exhibit identical behavior. This is because the program's code may instruct it to read only a fraction of its total available code. Consider all possible bit strings representing programs executed by universal equations. Programs that complete are naturally self-delimiting. They define their own length by virtue of reading only a finite number of bits. When the bits that are read are the same, the program behavior is the same, even when the rest of the unread part of the bit strings differ. If, for example, a program length is 9 bits, we can calculate that this program should appear once every 2 to the power of 9, or 512, bit strings. Self-delimited 10-bit programs would be half as common, appearing once every 2 to the power of 10, or 1024, programs. Conversely, 8-bit programs are twice as common as 9-bit ones. We can use this consequence of algorithmic information theory to make several predictions about the character of physical law. Quote, The main point is that the derivation is constructive, and it provides the technical means to derive physics from arithmetic. And this will make the computationalist hypothesis empirically testable, and thus scientific in the Popperian analysis of science. Bruno Marchal in the Computationalist Reformulation of the Mind-Body Problem, 2013. Confirming evidence. Could such a bold theory be true? For now, let's neither accept nor reject this theory. To do either before weighing the evidence would be premature. So let us not believe anything, and maintain an open mind. For the time, we will only play with the idea and see where it leads. As with any theory, the only path forward is to see what this theory predicts and then to compare the predictions with our observations. If we find it leads in a fruitful direction, by making predictions we can confirm and by not making predictions we can refute, then we will have cause to tentatively accept this theory. Predictions of the theory. Does the reality we see fit predictions of a reality generated by the infinite computations inherent to causeless arithmetical truth? For that matter, what are the predictions? At first blush, it seems impossible to get any useful predictions from a theory that includes all computations and all observations. For if they all exist, any observation is compatible with the theory. As Victor Stenger noted, theories that explain everything explain nothing. Fortunately, there is a catch: not all observations are equally likely. If our conscious states result from the existence of all computations, then they are subject to the rules of algorithmic information theory. This enables us to make testable predictions, and thereby tie it back to hard science, observation, and measurement. Some of the predictions of this theory provide clues to otherwise unsolvable questions in physics and cosmogony. These predictions offer answers to such fundamental mysteries as: why the universe obeys simple, mathematical, life-friendly laws. Why empiricism, i.e. experimental reproducibility, works. Why Occam's razor works. Why the laws appear fine-tuned for life. Why the laws are quantum mechanical. Why uncertainty and randomness exist in physics. Why infinite descriptions are needed to explain any occurrence. Why observation and information are fundamental in physics. And, why the universe has time and a beginning, for example, the Big Bang. These results are the work of pioneers in the theory, who include Bruno Marchal, Max Tegmark, Russell Standish, and Marcus Muller. Using the tools of computer science, math, information theory, and algorithmic information theory, they revealed how these traits of the universe result from our mind states being computationally generated. Quote: the appearance of a universe, or even universes, must be explained by the geometry of possible computations. Bruno Marchal in The Amoeba's Secret, 2014. Let's review the evidence for this most speculative of theories, which is presently at the forefront of mathematics and physics. Why laws? We take for granted that our universe obeys laws. But why should it? What's the source of these laws? Why are they so simple? Why aren't they ever violated? Why these laws and not others? All these questions are mysteries left unaddressed by science. Quote: in the orthodox view, the laws of physics are floating in an explanatory void. Ironically, the essence of the scientific method is rationality and logic. We suppose that things are the way they are for a reason. Yet when it comes to the laws of physics themselves, well, we are asked to accept that they exist reasonlessly. End quote. Paul Davies in the Flexi Laws of Physics, 2007. Quote: with the equations, when they are not too complicated, we can predict phenomena. But in truth, the equation doesn't explain anything. It compresses, certainly, in a very ingenious way, the description of the physical world. But it does not explain the nature of bodies nor why these bodies obey laws, nor from where these laws come. End quote. Bruno Marchal in The Amoeba's Secret, 2014. That laws are never violated, on its face, seems highly improbable. For in the space of possibility, for each way there is for the universe to obey the laws, there are infinite ways it might deviate from them. Quote. For each law-governed world, there are countless variants that would fail in different ways to be wholly law-governed. Derek Parfit in Why Anything? Why This? 2008. Why the laws hold is unknown to science. And yet, this feature of reality is the very basis that allows us to do science. A lawful universe is the basis of empiricism. It is why we can repeat experiments and make predictions about the future based on past observations. But why does this work, and why should it work? Marchal explains the emergence of laws as a consequence of the computational reality. He says the laws are the consistent extensions of programs that produce the observer's mind state. Quote. Arithmetic contains or executes all computations. Your first person is distributed on all computations going through your current first person state. To make any prediction on the future of your possible inputs, you need to take all the computations into account, and the laws of physics is what is invariant in all consistent extensions. Bruno Marchal in Discussion List, 2019. Muller goes further, and gives a mathematical proof that shows why, given algorithmic information theory, observers will, with high probability, observe a persistence of regularities, i.e. laws. Quote. That is, computable regularities that were holding in the past tend to persist in the future. Intuitively, highly compressible histories are those that contain regularities which can be used to generate shorter descriptions. Marcus Muller in Law Without Law, From Observer States to Physics via Algorithmic Information Theory, 2020. Because most programs are simple, and simple programs tend to keep doing what they have been doing, this gives the appearance of a fixed set of laws that holds into the future as the program unfolds. So in a sense, the laws of physics are the rules of the programs that instantiate us, as seen by those of us inside those programs. Why the laws are mathematical. It has long been recognized that mathematics is unreasonably effective in describing the physical laws. In 1623, Galileo wrote, "The universe is written in the language of mathematics." This connection between math and physics still puzzles scientists. Quote, "The miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. We should be grateful for it and hope that it will remain valid in future research and that it will extend, for better or for worse, to our pleasure. Even though perhaps also to our bafflement. To wide branches of learning." End quote. Eugene Wigner in The Unreasonable Effectiveness of Mathematics in the Natural Sciences, 1960. Mathematical patterns appear everywhere in nature. But why should physics be so mathematical? Tegmark offers a simple explanation: because physical theories result from our perceptions of what are ultimately mathematical structures. Quote, "The various approximations that constitute our current physics theories are successful because simple mathematical structures can provide good approximations of how a self-aware substructure will perceive more complex mathematical structures. In other words, our successful theories are not mathematics approximating physics, but mathematics approximating mathematics." End quote. Max Tegmark in Is the Theory of Everything Merely the Ultimate Ensemble Theory? 1998. Why the laws are simple. In the 2nd century, Ptolemy wrote, "We consider it a good principle to explain the phenomena by the simplest hypothesis possible." This rule of thumb is called the law of parsimony or Occam's razor. It is the idea that in science, the simplest answer that fits the facts is usually right. Occam's razor is no doubt a useful and effective rule, but until recently no one understood why it works. What is striking about the great questions of physics is their simplicity. Deep truths of nature can be expressed by short formulas, like F equals ma, and E equals mc squared. Physical equations rarely involve more than a few terms, rather than dozens or hundreds. Physicists are awestruck by this simplicity. Einstein remarked, "The eternal mystery of the world is its comprehensibility." Given there are far more ways for these formulas to be more complex, it's especially odd that they should be so simple. Quote, "Compared with simple laws, there is a far greater range of complicated laws. We would have some reason to believe that there are at least two partial selectors, being law-governed and having simple laws." Derek Parfit in Why Anything? Why This? 2008. Quote, "But the lesson is that, at present, the idea that the ultimate laws are as simple as possible is a hope, not something suggested by the evidence. Moreover, the prospect still faces the challenge of explanatory regression, as one would be left to explain why the underlying laws should be so simple." Sean Carroll in Why Is There Something, Rather Than Nothing? 2018. The mystery of simple comprehensible laws can now be answered. We have found a selector that preferentially selects universes with simple laws. Algorithmic information theory tells us that for each bit saved in a program's description, its occurrence is double. This adds up fast. A program that's 30 bits shorter, say 120 bits versus 150 bits, occurs 2 to the power of 30, or over 1 billion, times more often. Ray Solomonoff, the father of algorithmic information theory, was the first to draw a connection between AIT and Occam's razor. Quote, "On a direct intuitive level, the high a priori probability assigned to a sequence with a short description corresponds to one possible interpretation of Occam's razor." End quote. Ray Solomonoff in A Formal Theory of Inductive Inference, 1964. When Muller applied algorithmic information theory to observer states, he found that it led to the prediction of simple physical laws. Quote, "Observers will, with high probability, see an external world that is governed by simple, computable, probabilistic laws." End quote. Marcus Muller in Law Without Law, From Observer States to Physics via Algorithmic Information Theory, 2020. Why the laws are life-friendly. One of the most surprising discoveries in physics of the past 50 years was the discovery that the laws of physics and constants of nature appear specially selected to allow complexity and life to arise. Wheeler wrote, "A life-giving factor lies at the center of the whole machinery and design of the world. That the constants of nature, the strengths of the forces, the particle masses, etc., are just right to permit complex structures to arise is mysterious. Why are the laws this way? Why are they life-friendly?" Physicists ask, why does the universe appear fine-tuned? Quote, "As we look out into the universe and identify the many accidents of physics and astronomy that have worked together to our benefit, it almost seems as if the universe must in some sense have known we were coming." Freeman Dyson in Energy in the Universe, 1971. Quote, "The fine-tunings, how fine-tuned are they? Most of them are 1% sort of things. In other words, if things are 1% different, everything gets bad. And the physicist could say maybe those are just luck. On the other hand, This cosmological constant is tuned to 1 part in 10 to the power of 120, 120 decimal places. Nobody thinks that's accidental. That is not a reasonable idea, that something is tuned to 120 decimal places just by accident. That's the most extreme example of fine-tuning. End quote. Leonard Susskind in What We Still Don't Know, Are We Real? 2004. The first step in explaining fine-tuning is to recognize that for any universe to be perceived, requires that it be populated with conscious observers. This reasoning is known as the anthropic principle. The next step is to explain why any universe exists that supports conscious observers. Typical answers are that the universe was either designed or it is just one among a vast set of mostly dead universes. Quote, "We imagine our universe to be unique, but it is one of an immense number, perhaps an infinite number, of equally valid, equally independent, equally isolated universes. There will be life in some, and not in others." Carl Sagan in Pale Blue Dot, 1994. The existence of infinite computational histories guarantees that some will be of a type that can support life. Moreover, algorithmic information theory tells us the resulting physics should be maximally simple while respecting the constraint of being life-friendly. Quote, "In this paper I show why, in an ensemble theory of the universe, we should be inhabiting one of the elements of that ensemble with least information content, that satisfies the anthropic principle. This explains the effectiveness of aesthetic principles, such as Occam's razor in predicting usefulness of scientific theories." End quote. Russell Standish in Why Occam's Razor, 2004. And indeed, this is what we find when we examine our physics. Quote, "A very interesting question to me is the universe more complicated than it needs to be to have us here? In other words, is there anything in the universe which is just here to amuse physicists? It's happened again and again that there was something which seemed like it was just a frivolity like that, where later we've realized that in fact, no, if it weren't for that little thing we wouldn't be here. I'm not convinced actually that we have anything in this universe which is completely unnecessary to life." Max Tegmark in What We Still Don't Know, Why Are We Here? 2004. C. Is the universe fine-tuned? Why quantum mechanics? Quantum mechanics is a cornerstone theory of modern physics. It's among the most thoroughly tested of all theories in science, and it's given us the most accurate predictions in all of physics. But quantum mechanics is incredibly strange. It suggests the existence of many, infinite, histories, i.e. many worlds or many minds. Observation or measurement appears to cause the infinite set of possibilities to collapse to just one of the possibilities, and the selected result is absolutely unpredictable. According to quantum mechanics, no one can predict whether a photon will be reflected by or transmitted through a piece of glass, not even in principle. It's fundamentally random. Quantum mechanics includes apparent absurdities, like unobserved cats being simultaneously alive and dead, non-local faster-than-light influences, and unlimited computation underlying physical reality. Quote, "I have never been able to let go of questions like, how come existence? How come the quantum?" End quote. John Archibald Wheeler in Geons, Black Holes, and Quantum Foam, 1998. Of the mysteries in physics, how come the quantum ranks highly? Niels Bohr said, "Those who are not shocked when they first come across quantum theory cannot possibly have understood it." Werner Heisenberg admits, "I repeated to myself again and again the question, can nature possibly be so absurd as it seemed to us in these atomic experiments?" And Richard Feynman said, "I think I can safely say that nobody understands quantum mechanics." Wheeler thought if an ultimate theory could explain quantum mechanics, it would be a sure sign the theory was on the right track. Quote, "The most important test is whether it gives anything like quantum mechanics. If it does, we have a go-ahead sign; if not, we have to revise our thinking." End quote. John Archibald Wheeler quoted in Trespassing on Einstein's Lawn, 2014. Marshall's 1998 thesis, Computability, Physics, and Cognition, gave the first hints that features of quantum mechanics, such as indeterminism, the many parallel histories, the non-clonability of matter, and quantum logic, could be explained as a consequence of computationalism. Quote, "As in quantum mechanics, computationalism highlights a strong indeterminism, as well as a form of non-locality. Computationalism entails the existence of a phenomenology of many worlds or parallel states." End quote. Bruno Marshall, translated from Computability, Physics and Cognition, 1998. Marshall writes, "The quantum empirical clues happen to be serious hints that the physical emerges from an internally defined statistics on the numbers, dreams or computations, seen from inside." Standish went further. In a 2004 paper and in his 2006 book, he showed one could derive the basic rules, or postulates, of quantum mechanics, including the Schrödinger equation, purely from basic assumptions about observation within an infinite set of possibilities. Quote, "The explanation of quantum mechanics as describing the process of observation within a plenitude of possibilities is for me the pinnacle of achievement of the paradigm discussed in this book. I can now say that I understand quantum mechanics. So when I say I understand quantum mechanics, I mean that I know that the first three postulates are directly consequences of us being observers. Quantum mechanics is simply a theory of observation." End quote. Russell Standish in Theory of Nothing, 2006. Irreducible randomness. One of the strangest features of quantum mechanics is the presence of irreducible randomness that creates absolute unpredictability. Compounding this strangeness is the fact that the equations of quantum mechanics are entirely deterministic. And yet, when a measurement is made, it seems the universe momentarily stops following these equations to randomly select one possibility to make real, from among the many possibilities present in the equations. This was a pill too hard for Einstein to swallow. He declared, "God doesn't play dice with the world." And in the end he never accepted it. The single electron double-slit experiment was voted the most beautiful experiment in physics. In this experiment, an electron is put into a superposition, where the electron exists in multiple locations at once. Then its location is measured. But when we measure the electron's location, it will appear in only one location, seemingly at random. Before measurement, it's impossible, even in theory, to predict where the electron will be. If we inhabit a computational reality, why do we see any randomness or unpredictability? Computations are perfectly predictable. Might this observation of randomness give us cause to doubt or rule out our being in a computational reality? The opposite is true. The existence of an infinite computational reality explains why we encounter absolute unpredictability. If only one computational history existed, observing randomness would be cause to dismiss the theory. But here there are infinite computational histories. Some of these histories will be similar to each other, some, so similar as to be almost indistinguishable. Since there are infinite computational histories, each observer's mind state can be found within infinite parallel computational histories. In a 1988 conference and in a 1991 paper, Mechanism and Personal Identity, Marshall explained how the appearance of randomness emerges from multiple instantiations of a single observer's mind. He calls the phenomenon first-person indeterminacy. Quote, "To predict the first-person observable outcome of any physical experiment, you have to assume that your current computational state will not be obtained in some other part of the universe, or the multiverse, with different output for your experience. Bruno Marchal in The Computationalist Reformulation of the Mind-Body Problem, 2013. In summary, no brain that belongs to multiple distinct universes, or computational histories, can ever be sure what it will see next. Multiple parallel histories contain identical instances of the same observer's mind state, or brain. A fundamental unpredictability and randomness will result from the observer's inability to determine which universe she's a part of, as she exists in all of them. Quote, "It is impossible for any observer to deduce with certainty on the basis of her observations and memory which world she is a part of. That is, there are always many different worlds for which being contained in them is compatible with everything she knows, but which imply different predictions for future observations." Marcus Muller in Could the Physical World Be Emergent Instead of Fundamental, and Why Should We Ask? 2017. So even in a fully deterministic reality, the existence of infinite histories makes the appearance of randomness inevitable. The physicist shining a photon at a piece of glass is in an infinity of histories where the photon will reflect, and is in an infinity of histories where the photon will pass through. The physicist can't tell which until after the experiment is performed and she learns the result. Ultimately, randomness stems from our inability to self-locate within the infinite sea of indistinguishable computational histories. Tegmark notes how randomness appears in deterministic processes. Quote, "It gradually hit me that this illusion of randomness business really wasn't specific to quantum mechanics at all. Suppose that some future technology allows you to be cloned while you're sleeping, and that your two copies are placed in rooms numbered 0 and 1. When they wake up, they'll both feel that the room number they read is completely unpredictable and random." End quote. Max Tegmark in Our Mathematical Universe, 2014. Einstein is vindicated. God doesn't play dice with the world. But perhaps, not even God can predict what universe you will find yourself in once you perform a measurement that splits yourself. See, does everything that can happen, actually happen? Infinite complexity. In 1948, Richard Feynman developed the path integral formulation, which provided a new way to understand quantum mechanics. Feynman showed that you get the same results quantum mechanics predicts by taking into account and adding up every one of the infinite combinations of possible particle paths and interactions. It was bizarre, but it worked. And this new formulation provided key insights that helped develop quantum electrodynamics, or QED. In 1965, Feynman, together with Shinichiro Tomonaga and Julian Schwinger, shared the 1965 Nobel Prize in Physics for developing QED. But why adding up all of these infinite possibilities gave the right answers presented a great puzzle, which bothered Feynman. Quote, "It always bothers me that, according to the laws as we understand them today, it takes a computing machine an infinite number of logical operations to figure out what goes on in no matter how tiny a region of space, and no matter how tiny a region of time. How can all that be going on in that tiny space? Why should it take an infinite amount of logic to figure out what one tiny piece of space/time is going to do?" Richard Feynman in The Character of Physical Law, 1965. Under quantum mechanics, an infinite number of things happen behind the scenes. The smaller the scales you look, the more seems to be happening, with no bottom in sight. The appearance of infinite happenings, infinite computations and infinite logical operations underlying physical reality is mysterious. Perhaps the simplest answer for why reality appears this way is, it appears this way because that is the way reality is. If infinite computational histories form the foundation of reality, then infinities in physics might just be a reflection of this reality. Quote, "In short, within each universe all observable quantities are discrete, but the multiverse as a whole is a continuum. When the equations of quantum theory describe a continuous but not directly observable transition between two values of a discrete quantity, what they are telling us is that the transition does not take place entirely within one universe. So perhaps the price of continuous motion is not an infinity of consecutive actions, but an infinity of concurrent actions taking place across the multiverse. End quote. David Deutsch in The Discrete and the Continuous, 2001. Quote, "Matter is only what seems to emerge at infinity from a first-person plural point of view, defined by sharing the computations which are infinitely multiplied in the Universal Dovetailer's work, when persons look at themselves and their environment below their substitution level. The non-cloning results from the fact that such a matter emerges only from an infinity of distinct computations." End quote. Bruno Marchal in The Computationalist Reformulation of the Mind-Body Problem, 2013. Quantum computers. Richard Feynman and David Deutsch are the two fathers of the quantum computer. Feynman proposed their possibility in 1982, and in 1985, Deutsch described how to build one. These computers exploit the unlimited complexity inherent in quantum mechanics to build computers of incredible power. How quantum computers do what they do is puzzling. Each qubit added to a quantum computer doubles its power. A quantum computer with 300 qubits can simultaneously process 2 to the power of 300 states. This number of states exceeds the 2 to the power of 265 atoms in the observable universe. How could a tabletop device process more states than there are atoms? How could it solve problems that no conventional computer could solve in the lifetime of the universe, even if all matter and energy in the observable universe were recruited for that purpose? Some found the abilities of these computers so incredible, they concluded quantum computers simply weren't possible. After all, where exactly would all that computation be occurring? Deutsch and Tegmark offer some answers. Quote, "Since the universe as we see it lacks the computational resources to do the calculations, where are they being done? It can only be in other universes. Quantum computers share information with huge numbers of versions of themselves throughout the multiverse." David Deutsch in Taming the Multiverse, 2001. Given engineering challenges, for decades quantum computers remained only theoretical. Today, quantum computers are a reality. In 2019, engineers at Google reported that their 53-qubit quantum computer solved in 200 seconds a problem that would take the world's most powerful supercomputer 10,000 years. Today, anyone can sign up for free to program and use IBM's quantum computers over the internet. What makes quantum computers difficult to build, is that to work, they must be completely isolated from the environment, such that they are not measured by anyone or anything until it finishes its work. By isolating the quantum computer from the environment, observers temporarily make their existence compatible with all the possible states the quantum computer might simultaneously be in. The parallel computations performed by quantum computers can then be explained by the work of parallel computational histories. Quote, "If current efforts to build quantum computers succeed, they will provide further evidence for the quantum multiverse, as they would, in essence, be exploiting the parallelism of the quantum multiverse for parallel computation." End quote. Max Tegmark in Parallel Universes, 2003. C. How do quantum computers work? Why time? The universe, our lives, and even our thoughts are inextricably linked with the march of time. Few things are as familiar to us as time, and yet time remains little understood. See, what is time? 2,500 years ago, Heraclitus recognized change to be the only constant in life, saying, "All entities move and nothing remains still." But it doesn't seem logically necessary for a universe to have time. Quote, Mathematical structures are eternal and unchanging, they don't exist in space and time, rather, space and time exist in some of them. If cosmic history were a movie, then the mathematical structure would be the entire DVD. Max Tegmark in Our Mathematical Universe, 2014. Why should our universe have a property like time? All computers process information in an ordered sequence of steps. This ordering defines a notion of time that exists for any computation. Quote, "A Turing machine requires time to separate the sequence of states it occupies as it performs a computation." End quote. Russell Standish in Why Occam's Razor, 2004. Muller further showed that with algorithmic information theory, we can predict the appearance of a universe that evolves in time. Quote, "Our theory predicts that observers should indeed expect to see two facts which are features of our physics as we know it. First, the fact that the observer seems to be part of an external world that evolves in time, a universe. And second, that this external world seems to have had an absolute beginning in the past, the Big Bang." Marcus Muller in Could the Physical World Be Emergent Instead of Fundamental, and Why Should We Ask? 2017. Assuming we are part of an unfolding computation, then we should expect to find ourselves in a universe with time. A beginning in time? Current evidence suggests our universe has a beginning. But why should it? Until the middle of the 20th century, most scientists believed the universe was infinitely old, without a beginning. They considered theories of an abrupt creation event to be inelegant. Accordingly, scientists resisted the idea of a beginning until overwhelming evidence came out in its favor. It wasn't until we could actually see the afterglow of the Big Bang, in the form of microwaves, that scientists were convinced the universe began a finite time ago. We call this point the beginning because in tracing the history of the universe backwards, we hit a point where predicting earlier states breaks down and further backwards tracing becomes impossible. The physics either stops providing sensible answers, or we run into an explosion of possibilities and can't tell which of them is real. The theory of cosmic inflation gives an account of what caused the hot, dense, early phase of the universe. See, what caused the Big Bang. But inflation makes further backwards prediction, or retrodiction, impossible. It wipes its footprints with a set of infinite prehistories. Quote, "Since our own pocket universe would be equally likely to lie anywhere on the infinite tree of universes produced by eternal inflation, we would expect to find ourselves arbitrarily far from the beginning. The infinite inflating network would presumably approach some kind of a steady state, losing all memory of how it started. So the statistical predictions for our universe would be determined by the properties of this steady state configuration, independent of hypotheses about the ultimate beginning." End quote. Alan Guth in Eternal Inflation, Implications, 2013. Muller shows that algorithmic information theory predicts most observers will find themselves in a universe with simple initial conditions and an absolute beginning in time. He explains this reasoning for a hypothetical observer named Abby. Quote, "If she continues computing backwards to retrodict earlier and earlier states of her universe, she will typically find simpler and more compact states, with measures of entropy or algorithmic complexity decreasing, simply because she is looking at earlier and earlier stages of an unfolding computation. At some point, Abby will necessarily arrive at the state that corresponds to the initial state of the graph machine's computation, where simplicity and compactness are maximal. At this point, two cases are possible: either Abby's method of computing backwards will cease to work, or Abby will retrodict a fictitious sequence of states before the initial state, typically with increasing complexity backwards in time." End quote. Marcus Muller in Law Without Law, From Observer States to Physics via Algorithmic Information Theory, 2018. This mirrors what cosmic inflation does for our universe. In an alternate history where humans developed algorithmic information theory before microwave telescopes, we might have predicted a beginning of the universe before telescopic evidence came in. Information as fundamental. Physicists are increasingly recognizing that information plays a fundamental role in physics. Scientists have long understood that matter and energy can be neither created nor destroyed. They are, in all interactions, conserved. But only recently have physicists realized the same is true for information. Physical information can neither be copied nor deleted. There is an equivalent law for the conservation of information. This discovery stemmed from the black hole information paradox. According to general relativity, dropping something into a black hole destroys its information, like an ultimate furnace. But according to quantum mechanics, information can't be destroyed. At best, a black hole can only rearrange information, like an ultimate shredder. In 1981, this paradox sparked the black hole war, waged by two camps of physicists. After decades of debate, the black hole war settled in favor of quantum mechanics. Information can't be destroyed, not even by a black hole. Physicists now understand a kind of mass-energy information equivalence. There is also an equivalence between entropy in thermodynamics and entropy in information theory. And constants of nature are closely linked to the ultimate physical limits of computational speed, efficiency and storage density. See, how good can technology get? Why is the link between physics and information so tight? Wheeler dedicated his life to the pursuit of fundamental questions. Ultimately, he reached the conclusion that everything is information. Quote, "It from bit symbolizes the idea that every item of the physical world has at bottom, a very deep bottom, in most instances, an immaterial source and explanation. That which we call reality arises in the last analysis from the posing of yes-no questions and the registering of equipment-evoked responses. In short, that all things physical are information theoretic in origin." John Archibald Wheeler in Information, Physics, Quantum, The Search for Links, 1989. Quote, "Now I am in the grip of a new vision, that everything is information. The more I have pondered the mystery of the quantum and our strange ability to comprehend this world in which we live, the more I see possible fundamental roles for logic and information as the bedrock of physical theory." John Archibald Wheeler in Geons, Black Holes, and Quantum Foam, 1998. Why is information fundamental? The answer is easy if reality is computational. Information lies at the heart of computation. In the end, all that computers do is process information. So to say, computation is the foundation of reality, is another way of saying, information processing is the foundation of reality. Quote, "The burgeoning field of computer science has shifted our view of the physical world from that of a collection of interacting material particles to one of a seething network of information." End quote. Paul Davies in the Flexi Laws of Physics, 2007. Quote, "What we can learn from these reconstructions is that a few simple and intuitive constraints on encoding and processing of information will automatically lead to aspects of the Hilbert space formalism of quantum theory." End quote. Marcus Muller in Law Without Law, From Observer States to Physics via Algorithmic Information Theory, 2019. Observation as fundamental. Observation also appears to have a fundamental role in reality. Quote, "The universe and the observer exist as a pair. The moment you say that the universe exists without any observers, I cannot make any sense out of that. You need an observer who looks at the universe. In the absence of observers, our universe is dead." End quote. Andrei Lind in Does the Universe Exist If We're Not Looking? 2002. Quantum mechanics revealed that observation somehow forces reality to choose from among many possibilities. More recently, physicists have speculated that the observer's power to force reality's hand applies not only to the here and now, but perhaps all the way back to the beginning of the universe. Quote, "We are participators in bringing into being not only the near and here but the far away and long ago. We are in this sense, participators in bringing about something of the universe in the distant past." End quote. John Archibald Wheeler in The Anthropic Universe, 2006. Quote, "The top-down approach we have described leads to a profoundly different view of cosmology, and the relation between cause and effect. Top-down cosmology is a framework in which one essentially traces the histories backwards, from a space-like surface at the present time. The no-boundary histories of the universe thus depend on what is being observed, contrary to the usual idea that the universe has a unique, observer-independent history. In some sense, no-boundary initial conditions represent a sum over all possible initial states." End quote. Stephen Hawking and Thomas Hertog in Populating the Landscape, A Top-Down Approach, 2006. "The observer might even, in some sense, choose the laws of physics." Quote, "It is an attempt to explain the Goldilocks factor by appealing to cosmic self-consistency. The bio-friendly universe explains life even as life explains the bio-friendly universe. Cosmic bio-friendliness is therefore the result of a sort of quantum post-selection effect extended to the very laws of physics themselves." End quote. Paul Davies in The Flexi Laws of Physics, 2007. "Can there be a universe if there is no one to call it home? Do observations themselves somehow define the histories and laws of the universes containing them? Observation and its relation to observed reality is an enigma. Wheeler believed the relation between them was our best clue to finding an answer to why there is something rather than nothing." Quote, "Omnibus ex nihil ducendis sufficit unum," Leibniz told us, "for producing everything out of nothing one principle is enough." Of all principles that might meet this requirement of Leibniz, nothing stands out more strikingly in this era of the quantum than the necessity to draw a line between the observer-participator and the system under view. The necessity for that line of separation is the most mysterious feature of the quantum. We take that demarcation as being, if not the central principle, the clue to the central principle in constructing out of nothing everything. John Archibald Wheeler in Quantum Theory and Measurement, 1983. In the view that all computational histories exist, observation does play a role in selecting both histories and physical laws. It is a tautology that observers only find themselves in computational histories capable of producing their observations. Since every imaginable program exists, implementing every imaginable set of laws, then in a very real sense, the observer does force reality to select both the laws and history they observe. Quote, "To derive the effective laws of physics, one needs to do statistics over the ensemble of identical observers. This involves performing summations over the multiverse, but these summations are with a constraint that says that some given observer is present." End quote. Saibal Mitra in Discussion List, 2018. It's curious that Buddhist thinkers reached similar conclusions about observers well ahead of modern physicists. Quote, "The Buddhist does not believe in an independent or separately existing external world, into whose dynamic forces he could insert himself. The external world and his inner world are for him only two sides of the same fabric, in which the threads of all forces and of all events, of all forms of consciousness and their objects are woven into an inseparable net of endless, mutually conditioned relations." End quote. Anagarika Govinda in Foundations of Tibetan Mysticism, 1969. Reviewing the Evidence. we have found evidence in support of this theory. The existence of infinite computational histories predicts many features of reality. It predicts a universe of inviolable, but simple, mathematical, and life-friendly laws. It predicts a multiverse of parallel histories, infinite computational complexity, and a fundamental unpredictability, as we find in quantum mechanics. The theory predicts a universe that evolves in time, has simple initial conditions, and a point that we can't retrodict beyond, a beginning. Further, it predicts information and observation are fundamental. So far, all of these predictions are confirmed by current physical and cosmological observations. For the first time in history, humanity has an answer to why we exist that is backed by physical evidence. Conclusions? Given the observational evidence, we have reason to suspect that this theory, or something close to it, is correct. It implies, we live within the total set of all computations. Moreover, we have traced the existence of this set to something that's a strong candidate for having necessary existence, self-existent truths concerning numbers and their relations. Quote, "One option, following Leibniz and others, is that we reach a level at which further explanation is not required, because something is necessarily true." Sean Carroll in Why Is There Something, Rather Than Nothing? 2018. This truth not only seems causeless, but because from it we can deduce much of physics, it is also a candidate for being the cause. Quote, "The supreme task of the physicist is the discovery of the most general elementary laws from which the world picture can be deduced logically." Max Planck in Where Is Science Going? 1932. Under this theory, the most general laws from which we can deduce the world picture become the laws of arithmetic. Thus, arithmetic, as a theory of arithmetical truth, becomes a theory of everything. This brings a whole new meaning to Leopold Kronecker's edict, "God made the integers, all else is the work of man." Quote, "This is why, with Church's thesis, and the quantum confirmation of the mechanism, intuitive arithmetic, aka number theory and its intentional variants, may well be the simplest and richest theory of everything that we can have at our disposal." Bruno Marchal translated from Computability, Physics and Cognition, 1998. This theory, arithmetic, has been under our noses the whole time. Quote, "Behind it all is surely an idea so simple, so beautiful, so compelling, that when, in a decade, a century, or a millennium, we grasp it, we will all say to each other, how could it have been otherwise? How could we have been so stupid for so long?" John Archibald Wheeler in How Come the Quantum? 1986. The journey here. It's been a long road to reach the point where humanity can scientifically address the question, why does anything exist? Humans have walked the earth for some 500,000 years. But only in the last 1% of that time, or the past 5,000 years, have we had writing. Only in the last 0.1% of that time, or the past 500 years, have we had the scientific method. And only in the past 0.01% of that time, or the past 50 years, has humanity known about universal equations. To get an answer to our question, required that humans discover numbers, equations, computation, and wrestle with topics at the foundation of mathematics, including consistency, completeness, and decidability. In the end, this led to our discovery of universal equations that define all computation. To find evidence linking this computational reality to physics, humans had to discover the expanding universe and gather evidence of the Big Bang. We also had to probe the smallest scales and through careful study of particles, discover the quantum nature of reality. A century ago, we had none of this understanding. A strange answer. We can't help but notice how strange this answer is. But perhaps we should have expected this. Would we expect that the final answer to the greatest mystery of the cosmos would be ordinary? Quote. Now, my own suspicion is that the universe is not only queerer than we suppose, but queerer than we can suppose. J.B.S. Haldane in Possible Worlds and Other Essays, 1927. Quote. Whatever may be the truth about the universe, it is bound to be astonishing. Bertrand Russell. Quote. We will first understand how simple the universe is when we recognize how strange it is. John Archibald Wheeler in Geons, Black Holes, and Quantum Foam, 1998. Tegmark cautions against rejecting theories just for being weird. And admits he would be disappointed if the answer weren't a bit weird. Quote. It's very important for us physicists to not dismiss ideas just because they are weird, because if we did we would have already dismissed atoms, black holes, and all sorts of other marvelous things. And actually, when you ask a basic question about the nature of reality, don't you expect an answer which is a bit weird? I think anything but weird would be a big letdown. End quote. Max Tegmark in What We Still Don't Know, Are We Real? 2004. A Triumph of Human Reason. Quote. I believe when the history of science is written, then what's being discovered about our universe in the last decade or two will be one of the most exciting chapters. End quote. Martin Rees in What We Still Don't Know, Are We Real? 2004. We now have viable answers to great questions of existence. Leibniz's question, why is there something rather than nothing? Einstein's question, why is the universe so comprehensible? Wigner's question, why is the universe so mathematical? Wheeler's question, how come the quantum? Smolan's question, why these laws and not others? Feynman's question, why does infinite logic underlie physics? Hawking's question, what breathes fire into the equations? It required us to assume math, rather than matter, is fundamental. Given the evidence supporting this view, we might consider the 2,400-year-old debate between Plato and Aristotle as settled. Quote. If we do discover a complete theory, it should in time be understandable in broad principle by everyone, not just a few scientists. Then we shall all, philosophers, scientists, and just ordinary people, be able to take part in the discussion of the question of why it is that we and the universe exist. If we find the answer to that, it would be the ultimate triumph of human reason, for then we should know the mind of God. Stephen Hawking in A Brief History of Time, 1988. Hawking believed if could discover what breathes fire into the equations, then we should know the mind of God. But, do we? By postulating infinite, eternal, mathematical truth as the ultimate explanation, and the cause and source of reality, have we succeeded in explaining God, or have we explained God away? Open questions. While this theory provides answers to many questions, it does not answer everything, and much additional work is required. Room for God. This theory provides a purely natural and rational account for why anything exists. Is there any room for God in this picture? We now have a view of reality where everything emerges from absolute truth. This infinite truth embodies all knowledge. Being a container of all knowledge, as well as all minds and things, can we compare this infinite set of truth to an omniscient mind? This truth is infinite and incomprehensible, eternal and indestructible, without a beginning or end. It is uncreated and self-existent. It is transcendent, immaterial, immanent, and indivisible. It's the reason and cause behind all things. It serves as the creator, source, and ground of being, supporting us and the material universe. Does this infinite truth or omniscient mind lead to the existence of God? Might it even be God? It's not a simple question. But knowing why anything exists, leaves us in a better position to answer questions about what exists and what doesn't. C. Does God exist? Deriving physical law. How much of physical law can we derive from the assumption of all computations together with the requirement of life-friendliness? Can we predict things like types of particles and forces, or the dimensionality of spacetime? Might we even be able to predict values of constants like particle masses and force strengths? Quote, "What really interests me is whether God could have created the world any differently. In other words, whether the requirement of logical simplicity admits a margin of freedom." End quote. Albert Einstein. It remains to be seen how much of physical law is universal, applying to all observers in all computational histories, and how much is geographical, depending on which histories an observer belongs to. Quote, "As a theoretical physicist, I would like to see us able to make precise predictions, not vague statements that certain constants have to be in a range that is more or less favorable to life. I hope that string theory really will provide a basis for a final theory and that this theory will turn out to have enough predictive power to be able to prescribe values for all the constants of nature including the cosmological constant. We shall see." End quote. Steven Weinberg in Dreams of a Final Theory, 1992. But this hope, of deriving every aspect of physics, is waning. Max Tegmark recounts, as recently as 1997, the famous string theorist Ed Witten told me that he thought string theory would one day predict how many times lighter an electron is than a proton. Yet when I last saw him at Andre Linde's 60th birthday party, in 2008, he confessed after some wine that he'd given up on ever predicting all the constants of nature. Implications. If all computations exist, and if those computations explain our observed reality, it leads to many surprising implications. The universe is a dream. The theory lends support to the ancient idea, expressed by Taoist, Greek, and Christian philosophers, and a tenet of Hindu and Buddhist belief, that the material universe is a kind of dream or illusion. It implies that the material and physical are byproducts of mind. Quote, "Collective karmic impressions, accumulated individually, are at the origin of the creation of a world. The outside world appears as a result of the acts of sentient beings who use this world. The creator of the world, basically, is the mind." The 14th Dalai Lama in Beyond Dogma, 1994. Quote, "For the things which one thinks are most real, are the least real." Plotinus in the Enneads 5:11, 270 AD. Only recently have modern scientists begun to embrace this view, with a few even doubting the realness of physical existence. Niels Bohr said, "Everything we call real is made of things that cannot be regarded as real." In an interview, Marvin Minsky admitted, "We don't know that we exist because maybe we're just what a program would do if the computer were turned on and it's not even running." We live in a simulation. The simulation hypothesis and simulation argument raise the question of whether or not we inhabit a vast computer simulation. If we exist as a consequence of mathematical truth, the simulation hypothesis is made true by default. For we would then find ourselves living within the infinite set of computationally generated histories. This blurs the distinction between virtual reality and real reality. It remains an open question: is anyone in control of the simulation we happen to be in? C. Are we living in a computer simulation? Our place in reality. With an answer to why anything exists, we can orientate ourselves in reality. We now understand our position and place in it. Mathematical truth implies the existence of all computations. The existence of all computations implies the existence of all observers. The existence of all observers leads to a quantum mechanical reality populated with all possibilities and ruled by simple laws. So what exists? Almost everything. Reality becomes so big and so comprehensive that it includes everything and everyone that can be. Every thought that can be had and every experience. Every story and scenario plays out, eventually and somewhere. Actually, they all recur an infinite number of times. Indeed, in this view, reality is so large that it guarantees the existence of an afterlife. See, is there life after death? Quote. Confession: if I love this theory, it is because it entails the existence of many things not physically present. Notably those incredible deep universal dreamers which keep losing themselves in an incredible labyrinth of partially shareable dreams. Meeting ladders and ladders of surprises, self-multiplying, and self-fusing, and which are partially terrestrial and partially divine creatures. End quote. Bruno Marchal in Discussion List, 2011. Reasoned study of the mysteries of existence has brought us to a coherent theory of why there is something rather than nothing. The best evidence suggests our universe is one among an infinite number of possible realms, with the full extent of reality being unbounded. The source of this reality is logical necessity, via infinite mathematical truths which are independent of any material universe. We can count ourselves among the first generation of humans able to reason logically, with the support of observational evidence, to arrive at answers for why our universe has the laws it does, why we are here, and why there is something rather than nothing.